Hello, everyone, and thank you all for taking the time to listen to our presentation. We are the 2024 High Altitude Airship Project.
My name is Bárbara Lebrija, and I'm from Monterrey, Mexico.
My name is Brandon Lowe, and I'm from Bellevue, Washington.
My name is Mairead Meaney, and I'm from Wilmington, North Carolina.
My name is Katia Martinez, and I'm from Mission, Texas.
My name is Nguyen, and I'm from Sugar Land, Texas.
My name's Saanvi Pradhan, and I'm from Austin, Texas.
Hi, my name is Tait, and I'm from San Antonio, Texas.
I'm Jacob Toomey, and I'm from Allendale, New Jersey.
We would also like to thank Dr. Snowden and Mrs. Webb for their contributions to our project.
Our objective was to design, build, and test an airship in order to demonstrate its suitability for an extended study of Titan's surface and atmosphere.
We selected Titan because it is one of few celestial bodies in the solar system that has a dense enough atmosphere for an airship to fly. Titan is also a very interesting moon to explore, as even despite its toxic nitrogenous atmosphere, methane clouds, rivers, and lakes, and its extreme cold, there is still potential for life forms that use methane as a liquid solvent instead of water. Life as we know it couldn't exist, but if we were to discover life, it would revolutionize the fields of biology and astronomy, showing the potential for different life forms from all across the solar system and galaxy.
As lighter than air vehicles, airships are the ideal platform for a long-term mission to Titan. They rely on aerostatic rather than aerodynamic forces, which minimizes fuel consumption. Additionally, airships offer a unique combination of low-speed, low-altitude flight, endurance, and maneuverability. Finally, airships are able to capture high-quality data while covering a large land area, enabling analysis of Titan's hydrologic cycle, methane sources, and possible origins.
Before constructing the airship, we calculated some of the forces that would be acting on it. We found that considering the weight of the balloon, the airship would have a carrying capacity of around 0.38 kilograms, assuming a perfectly spherical balloon. We also calculated the estimated drag, finding that there would be about half a newton of force opposing the thrust from our motors.
Using the calculations from the previous slide, we determined that the total weight of our design had to be 0.516 kilograms, with the payload mass being less than 0.38 kilograms, and the minimum speed had to be 1.5 meters per second. The guidelines from our mentor and the program gave us 2 weeks to construct the design using a 0.368 meter radius balloon. With the criteria and constraints in mind, we moved into the sketching phase, where each team member sketched their own design for the airship. Some of the aspects we focused on were the shape of the gondola, the number of propellers, the propeller positions, and the method used to attach the gondola to the balloon. We then came together to compare designs and narrowed it down to 4 options.
Our first design idea relies on force components. Two motors enable horizontal movement. When both are run, sideways forces cancel, enabling forwards motion. To turn, only one motor needs to be run. An additional motor on the bottom of the airship enables vertical motion.
Our second idea consisted of 8 motors, pointing left, right, forward, backward, and down. Increasing or decreasing the thrust of certain propellers would allow the airship to move in all directions without turning. This was a simpler and more traditional approach to airship design, but having 8 propellers and motors raised concerns about weight.
Our next idea was modeled after a quadcopter drone. This would utilize 4 DC motors and attempt to replicate the flight dynamics of a drone to move the airship. The big advantage of this design is that it allows for strafing and horizontal movement without rotating the whole body. However, applying drone dynamics to a relatively large balloon platform would be a challenge given its greater inertia. Our final idea utilizes thrust vectoring. This is the most traditional approach to a gondola design out of the 4. 2 DC motors, each rotated by a positional servo, angle up and down and sideways to provide thrust. This approach would be the most simplistic because it is following traditional designs of a normal gondola. To decide which designs we should pursue, we created a decision matrix. Each design was graded based on a set of criteria, with the lower numbers as worst and the higher numbers as best. As you can see here, for attachment mechanisms, we decided on using a net instead of a rigid exoskeleton to attach our gondola to the balloon. This was largely because of the ease of doing so. For our gondola, we settled on the drone design as it was the most well-rounded and performed the best overall. And ultimately, we settled on our final design of a drone maneuvered by 4 DC motors, with the electronics placed in the center. The drone is 19 centimeters across and weighs about 29 grams once 3D printed.
For the electronic components, we chose to program an Adafruit featherboard and integrated a motor driver to control 4 DC motors. The motors were powered by 4 AA batteries, while a 3.7-volt lithium battery provided power to the featherboard itself. Attached to the featherboard was an SD card reader responsible for recording data from its onboard sensors, which included temperature, humidity, acceleration, and pressure to monitor environmental conditions. The featherboard operated wirelessly, enabling autonomous flight capabilities.
Using the previously shown diagram, we modeled the optimal placement of our electronics using fritzing. To conserve space and minimize weight in our final model, we positioned our motor driver above the featherboard, thus eliminating the need for a breadboard. Here on the left, you can see Barbara and myself soldering the heather pins to the featherboard to secure it into the driver during the testing process.
In terms of programming, we utilized an Adafruit featherboard that is equipped with the USB connector, charging port, and several different sensors. With the charging port, we were able to fly our airship wirelessly while using a battery, and with the USB connector, we were able to plug the board into a laptop and run code files from the CircuitPy drive we created. We ran and coded our programs in the CircuitPython environment called Mu, and from there, we were able to test the functions of our code, such as spinning the motors through the Bluefruit Connect app that contained a control pad, all of which was compatible with both our featherboard and CircuitPy. At first, we had some technical challenges connecting the board to our laptop and getting some of our programs to execute. But after we were able to troubleshoot those issues, we were able to implement several features on our airship, including movement and sensors. These sensors include an accelerometer, a gyro, which measures angular velocity, temperature, humidity, air pressure, altitude, proximity, sound, and more. As we tested our build in the air, all the different sensors collected data and stored it within a file within the SD card, which will be discussed in depth later.
After setting up the microcontroller, our main focus was coding the motors, done by utilizing CircuitPython and its MotorKit library. We were able to maneuver the airship vertically by switching the directions of the motors, which changed the airflow, causing the ship to push either up or down. However, our biggest challenge was changing the direction of the ship without causing it to drift upward as well, and integrating these quadcopter flight dynamics into a neutrally buoyant airship, a concept we couldn't find much past research on. After some experimentation, we accomplished this by referencing drone dynamics, running two adjacent motors at a high speed and running the other two at a low speed, causing the ship to move in the direction of the slower motors. Using the Bluefruit Connect app, we added a user interface to allow the ship to be maneuvered through a control pad. As you can see, the control pad included 4 directions: front, back, left, and right, and some additional controls such as stop, up and down, and 4 incremental settings for speed. One of the most important parts of the user interface is the 4th button, which allowed us to program when we wish to collect and store data. By clicking the button, a stream of data is stored to an SD card, including readings for temperature, pressure, sound, humidity, and acceleration, which can be later downloaded and analyzed. This was another one of the biggest challenges we faced throughout the project, determining an efficient way to collect data. After attempting to use an MQTT protocol, we eventually settled on the SD card due to its simplicity and efficiency.
We conducted several tests throughout our project as we made an increasing amount of process in terms of the code and design. Initially, we were able to test the motors at varying speeds ranging from 0 to 1, and we noticed that the motors created a significant amount of thrust able to easily lift their own weight. After we had received our 3D print, we were able to build our first prototype, which is pictured in the second image, where the 36-inch balloon filled with helium is oriented horizontally with the drone on the bottom center. We tried the net at first, but then decided against it, as it added too much mass to the airship, making it too heavy to be neutrally buoyant, deciding to use masking tape and Velcro to secure the build to the balloon. In our most recent prototype, which is in the third image, we oriented the balloon the way it normally is and found success in securing the drone at the bottom with a string that was tied around the balloon. After deciding that that particular design was the best, we added little increments of mass to the airship to make it neutrally buoyant, which allowed us to continue testing and controlling the movement of the airship with the motors.
Although we had performed some rough calculations prior to the build, we recalculated a lot of these numbers after initial testing. Due to the diameter of the balloon being smaller than expected and its ellipsoid shape, the true calculations came out to be much smaller than expected. Our final carrying capacity ended up being roughly 0.269 kg, significantly less than our estimated 0.38 kg.
Measurements made by the accelerometer show the airship's directional acceleration in 3D space. This data is useful to show both where the airship is going, as well as being used to calculate wind speeds on Titan.
Adding to that data, we were also able to collect data on the surrounding pressure and humidity over time and convert that to line graphs. Understanding these atmospheric conditions helps us understand the airship's flight for stable operation, and for landing on Titan, this data is crucial to navigate its dense atmosphere and ensure that we have a safe descent.
Throughout the course of this project, our team had to handle many challenges. Firstly, the initial calculations we made for lift force and terminal velocity weren't accurate because of the assumptions and estimations we made. This made it more difficult to make the airship neutrally buoyant. Secondly, the balloons were difficult to work with because they were delicate and would deflate by the end of each day. Finally, we had limited time since we only had 2 weeks in person and resources such as helium and 3D printed items were limited. If given unlimited time and materials, there are some improvements we would make to our design. We would include additional sensors and capabilities such as a camera, mapping capabilities, or a UV sensor. We would make sure to use precise measurements and calculations so we could know exactly what constraints we were working with. And if this were an actual mission to Titan, we would also include a shield to protect the electronics from Titan's harsh conditions, and we would deploy multiple airships for fault tolerance and increased data collection.
On behalf of the team, NASA SEAS has been incredibly impactful in not only providing the opportunity to engage in high-level research, but also the importance of perseverance. This experience has not only deepened my curiosity for science, but the trips along the way significantly improved the team's collaboration and created a positive environment which reflects on the quality and outcome of our work today. We give the deepest thanks to not only our mentors, but everyone behind the scenes that made this program possible.
Previously, I wanted to major in mechanical engineering, but this program has allowed me to explore a new career path, and I now plan to major in aerospace engineering.
I'm an aspiring aerospace engineering major, and this program has allowed me to learn about the NASA Pathways internship, which is a possibility for me in the future.
Working on the electronics portion of this project solidified my passion for engineering and made me capable of becoming an electrical engineer in the future.
I'm an aspiring aerospace or mechanical engineer major, and this program allowed me to gain experience with CAD and engineering design, both of which will be useful for me in the future.
I'm an aspiring electrical engineer or computer scientist, and this internship has allowed me to gain experience with programming and hardware, which will be useful to me in the future.
Participating in NASA SEAS gave me hands-on engineering experience, which I hope to later apply in the future as an electrical engineering major.
Through SEAS, I became more certain of my plans to become an aerospace engineer for NASA.
I'm an aspiring computer science and economics major, and through SEAS I learned that even though I don't want to be an engineer, there's still a place at NASA for people of all different skill sets.
Lastly, we again wanted to conclude by saying thank you to NASA SEAS for giving all of us this opportunity. Additionally, thank you to our team mentors, Dr. Darci Snowden and Ms. Sha'Rell Webb, for their support and guidance, which made our project a great learning experience. This internship was an amazing experience, and our favorite part of this amazing experience was getting to visit the Space Center in Houston and getting inspired by the great features achieved there.